Hi everyone, I'm Yuxin Ma, currently a postdoc from Vader Lab, Arizona State University. Here the second author, Arlen Fan, a PhD student in our lab. Today we're going to introduce our work on a visual analytics framework for explaining and diagnosing transfer learning processes. Knowledge transfer is a process where the existing knowledge learned before is reused in a new domain to finish new tasks. For example, an experienced car driver can learn to operate boats with less effort by mapping the control mechanism, or a pianist may master other musical instruments faster than new learners because of the shared music theory. In the context of machine learning, a meta strategy called transfer learning was proposed to reduce the cost of labeling new instances and minimize the threat of bias by relaxing the assumption of independent and identical distributions. In the deep learning community, transfer learning is considered as a promising approach to mitigate the issues of the high demand for labeled data and extremely long training time. One of the most commonly used transfer methods is called fine-tuning. The new model is first initialized with the trained network parameters in an existing model. Then, the model is further trained on a relatively smaller amount of training data instances for the new task. However, understanding the knowledge transfer process is a non-trivial task. Conventional model performance measures are not enough for demonstrating the robustness of the transfer process. In addition, model developers need to understand what knowledge has been transferred from the old model and how the knowledge is reused in a particular form in the new model to boost its performance, which lends themselves well in the visual analytics paradigm. Essentially, the core task here can be described as: how can we conduct effective comparison between the knowledge extracted from the existing dataset and the one in the new domain? Here, we call the existing and the new models as source and target models in their own learning task domains. So we can say that the knowledge is transferred from the source model to the target model. Some existing works have been proposed to support understanding of deep neural networks and comparison between models. However, there is still a need for integrating the analysis of knowledge transfer process in the interpretation of deep learning models in order to show the relationships between source and target models, as well as how knowledge is inherited in the target model. With the literature review and discussions with the domain experts, we propose three main analytical tasks from two perspectives: analytical complexity and data granularity. The tasks are organized in a hierarchical manner, from overall statistical measures of model performance down to the detailed inspection of data instances, core components in the deep neural networks, and the extracted features. For presenting the statistical measures for the source and the target models, we focus on overall prediction accuracies along the training epochs and the per-class accuracies. The overall accuracy chart provides a general measure of whether the target model performance is boosted or harmed by introducing the source model. The problems can be narrowed down to class level by checking the table of prediction accuracies for each class. The classification results can be inspected in the t-SNE projection result of embeddings of instances on the target model. Here, the colors of the points indicates the classes. The dots and crosses represent instances from the source and the target dataset. respectively. And the dark border means it is misclassified in the target model. When hovering the mouse pointer on a glyph, the details of the corresponding instance are listed, including the original image, the domain of origin, the ground truth label, and the prediction made by the target model. Besides the instances, we further examine the essential structures that best represent the learned pattern and knowledge hidden in the networks. When a class is specified, the neuron attribution and weight values for each instance are computed, resulting in vectors that characterize the behaviors of neurons and weights on the class. The neurons and weights are further divided into important and non-important groups based on how powerful they are in deciding the class labels. To compare the behaviors of neurons in the source and the target models, the pairwise distances are computed between the corresponding vectors, resulting in similarity matrices between neurons in the corresponding network layers in the two models. For how to visualize the network comparison result, I will pass it to Arlen.
The comparison between neurons and weights from two models are visualized in a matrix-based design. The similarity values between neurons are mapped to the brightness of matrix cells, and weights which join important neurons between two consecutive layers are rendered as adjacency matrices. To further show the results for non-important neurons, the user can toggle the extra regions in the matrices to view summaries of additional non-important neuron similarity values and weight values. Finally, we inspect how domain invariant or domain-specific the extracted features can be when considering neurons as feature extractors. Here, the neurons extracting domain-invariant features indicate that they carry common patterns shared in the source and target domains, which can be helpful in explaining what knowledge is reused in the target model. We have designed a measuring algorithm to compute the discriminability values by considering how important a neuron can be when distinguishing between instances from the source or the target domain. Two views are designed as well as to list the details of the most or least domain discriminative neurons and show how do these neurons separate the instances from the source and the target domains. In the case study, we explore how an AlexNet classification model on the Amazon product profile images can benefit the new model of classifying photos from web cameras. After loading the dataset, the statistical measures of the source and target models are displayed in the stat view. In the accuracy chart, the source model performs well on the source dataset with high training and validation accuracies. However, the accuracy of the source model in the target dataset is around 0.4. For the target model, it performs significantly better than the source model on the target dataset, while it has a slightly worse accuracy on the source dataset. In the class table, some classes receive the same high accuracies from both models, such as bike and calculator, while classes like file cabinet and phone have the most diverse performances between the two models. In the projection result of class bike, the images share similar characteristics, such as visual angles and the appearance of bikes. For file cabinet, the patterns of cabinets in the different photos vary significantly. When selecting file cabinet and desktop computer, we find that the distribution of instances from the two classes are overlapped without a clear boundary, indicating a high chance of causing misclassification. When activating the first and second layers of bike in the network relation view, we see that the indices of the most important neurons are similar on both sides. Many of the source neurons with the same indices are also the most similar neuron of their target counterparts. The phenomenon still exists in deeper layers, such as layer 7. However, the proportion of the important target weights with corresponding important source weights are different between shallow layers and deep layers. In the weights between layers 6 and 7, the proportion is significantly lower. The issue also happens in the class file cabinet, where such a difference happens in the weights between shallow layers such as 2 and 3. In the feature view, the top 3 most domain discriminative neurons show flat ellipses. In the domain discriminability plot, the images show a wide range of tire shapes, from circles to lines due to visual angles. Some low discriminability ranks depict patterns of handlebars and frames that exist in almost all images. To summarize our talk, we propose a visual analytics framework for inspecting and exploring transfer learning processes and a multi-aspect design for comparative analysis of models and data between domains. In the future, we would like to further extend the scalability of comparison algorithms and support industrial-level large-scale models. In addition, we will explore how different attribution methods influence the result, as well as how to support multiple source domains. Thank you for your interest. We are happy to take questions.